Okay, this is the first of the week 5 lectures, and this week we're sort of making the transition from the differential equations part of the course to the signals and systems part of the course. And in fact, by virtue of the fact that we've been using transform techniques to solve differential equations, we can make this transition relatively seamlessly. A key part of that transition is introducing the concepts of zero input and zero state responses. So for this, let's go back to our mass spring damper example that we saw near the very beginning of the course. So this mass spring damper system was modeled by this equation, which related the displacement y of the mass to an applied force F. Okay, so F of t we called the forcing term of our differential equation. And the problem was, given a forcing term and given initial conditions, say on y and its derivatives, to solve for y as a function of time. Now in the signals and systems course, we're going to talk about systems with inputs and outputs. And in this example, you might think of the applied force F of t, the forcing term, as representing an input to the system, and the resulting displacement y as a function of time as the output of the system. You apply a certain force as a function of time, and you get a certain displacement as a function of time. So the force is the input, the displacement is the output. We know that we can find what that output is going to be for a given force and for given initial conditions by applying the unilateral Laplace transform to every term in this differential equation. And if we do so, we will convert it to an algebraic equation, and we'll just have to solve algebra. We can write that equation out in this form here. And here what's been done is that the terms that depend on the forcing function, the term that depends on the forcing function, has been separated, if you like, from the term that depends on the initial conditions on y. And this is an important distinction that will enter into our approach to studying signals and systems. This first term is what you would get if the initial conditions were all zero. Any initial condition that had any bearing on the problem was set to zero. And for that reason, we call this term the zero state response, or you might say it's the transform of the zero state response. On the other hand, suppose f of t is always zero for all t, or for all t greater than or equal to 0. Then we know that the output y will just be the inverse transform of the second term here. And this term just depends on initial conditions. So for that reason, this is called the zero input response. When we study signals and systems, we're going to focus primarily on this zero state response. The idea in the signals and systems part of the course will in particular be to study the relationship between different inputs or forcing terms you could apply and the resulting outputs. In fact, as I've said before, the classical approach to differential equations, where you assume that the forcing term is given and say any relevant initial conditions are given, that corresponds to solving an analysis problem. This is the sort of thing that natural scientists are often interested in because these things are given in their case. If you're trying to analyze the motion of a planet, the forces are given by, say, the positions of other heavenly bodies and so on. And given those forces, you can try to solve for the motion of the planet. It gets more complicated than that, of course, because the planets affect each other and so on. But the idea is that you're just trying to find out what the behavior of a given system is. But we engineers, we have to try to design things. So instead of just saying for a given f of s, what is the resulting y of s, as given, say, by this zero state response. But often we know roughly what we want y of t or y of s to look like, and we have to try to find an input, f of t or f of s, that gives us an appropriate response. So rather than an analysis problem, this is what we might call a synthesis problem. And that means we have to be able to do more than just solve initial value problems. We need to understand the relationship between the input and the output of the system. And we will study that primarily by studying this so-called zero-state response. In particular, you see that in this framework, the relationship between f of s and y of s is just an algebraic one governed by this function here, by which you multiply f of s to get y of s if the initial conditions are 0. And in fact, this function is what we call the transfer function. So we'll be studying these transfer functions because they capture the relationship between inputs and outputs, and they'll let us solve things like the kind of synthesis problems that engineers are often interested in. So in order to lead into that systems and signals part of the course, I'd like to say a little bit more about some of the implicit assumptions that we've been basing our work on so far. So far we've been assuming that f of t, y of t, and any derivatives of those functions with the possible exception of the highest order derivatives that show up in the equation, are continuous. Why is that? Well, we've been talking about their derivatives. We've been talking about derivatives of f and y and all the derivatives other than the highest order ones. In order for those functions to be differentiable, they have to be continuous. We've implicitly assumed that the highest order derivatives only need to be piecewise continuous in order to apply our transform techniques. So it's going to be convenient to try to relax these assumptions. In order to do that, we are going to introduce what we call generalized functions. So we'll now relax these assumptions by introducing so-called generalized functions, which will play the role of derivatives of functions that are not necessarily continuous but may only be piecewise continuous. Now, a piecewise continuous function, like say a unit step, again, because it's not continuous, it doesn't have a derivative in the normal sense of the term. It has that jump at t equals 0, so it doesn't have an ordinary derivative. But these generalized functions will serve as a kind of derivative. In particular, for that case of the unit step, we'll have a generalized function called the unit impulse function. And we'll denote it by delta t. That will play the role of the derivative of the unit step. So we'll now be able to relax those assumptions that assume that f and y and all but the highest order derivatives were continuous. Moreover, this comes back to the notion of the zero state response. Introducing this unit impulse function will help to explain the significance let's say that it will also help, because it's not only going to let us relax the assumptions that we were using earlier, but it will also help to explain the significance of this transfer function. That determines the zero state response. So to sum up, going back to our first slide, we've been solving these initial value problems by making these assumptions that our functions and all but their highest order derivatives are continuous. We're now going to be able to relax that by introducing so-called generalized functions. And as we'll see, introducing such generalized functions, and in particular the unit impulse function, will help us better understand the form of this zero state response, and in particular what this so-called transfer function really is. So we'll start looking at the unit impulse function in the next lecture.